As you see behind me, video number 2 for this chapter, surface area, is this. How do you find the area of a pyramid? Look, it's in the pyramid shape. Oh, I love it. Okay, listen. The difference between this video and the last video, of course, this says pyramid, the other one says prism. So this should be going on your foldable, the second one up on your foldable. But remember this. These guys here were prisms. They had 2 bases, and they had all these lateral faces. That was a prism. This is a square prism, hexagonal prism, and a triangular prism, if you will. So we're talking now about pyramids, and as there were characteristics of prisms, there also are certain characteristics of pyramids. So here we go, on your foldable. Let's do it. So certain characteristics of pyramids is this. 1, characteristics will be this. Every single pyramid that we talk about have only 1 base. So the difference. Prism has 2 bases, and this particular pyramid right here, boop, boop, only has 1. That is the difference. 2 bases in a prism, 1 base in a pyramid. Now you all know what pyramids look like. Yes, walk like an Egyptian, I got you. So you know what they look like, but there's the first characteristic. They all have 1 base. The same concept though applies here in green. The base shape determines the name, just like a prism. So this guy right here, the base is a hexagon. That is a hexagonal pyramid. The base shape right here, woo, is a triangle. That is a triangular pyramid. The base shape right here, woo, is a square. It is a square pyramid, or a rectangular pyramid, depending on what you're talking about. And the base can be any shape it wants to be. It doesn't need to be a regular polygon. It could be anything. But the name of it determines the name of the base, the shape base, whatever, is the name of the actual pyramid itself. So that's the first most important thing. Along with that, you have non-parallel lateral edges. That's these things right here. I'll use my finger. That's a non-parallel lateral edge compared to this one. It's a lateral edge. But they all come together at a point up here. So you see, non-parallel lateral edges meet at one point, and that's called the vertex. So that's the vertex right there. The thing I'm holding on to, that's the vertex of this pyramid. That's the vertex of this pyramid. You get the idea. So all the lateral edges come together at the top, or the left, right, bottom, it doesn't matter, but that is the vertex. Third thing, the lateral faces will always be triangles. You can see in this one, they're all triangles, compared to this guy, of which they were all rectangles. So there's a difference. Pyramids have triangles as faces. These guys always have rectangles as faces. Okay? Let's keep on going. Hey, one other thing you got to remember or know is this. In terms of the base shape, if it's a regular polygon, guys, then the actual pyramid is called a regular pyramid. So if the pyramid has a base that is a regular polygon, so for example, like the one I just had right here, this triangle, that was an equilateral triangle. A regular polygon, I couldn't think of the word, a regular polygon. This is called a regular triangular, if you will, pyramid. This guy here, a regular hexagon. This would actually be called a regular hexagonal pyramid. Now, if it was just a hexagon on the base that wasn't a regular hexagon, then it would be called hexagonal pyramid. But since it's a regular hexagon, that's called a regular hexagonal pyramid. So there's just a simple little definition there. Hey, a couple things that's kind of cool about, though, a regular pyramid. Number 1 is this. The lateral edges are all congruent. It's pretty cool. And the other thing is the lateral faces are all going to be congruent isosceles triangles. Remember that, because that might come into play in a couple examples when we find the lateral surface area of the pyramids themselves. The lateral surface area and total surface area. So, let's rock and roll. A couple other characteristics, guys, about pyramids. Number 4, every single pyramid has this thing called an altitude. Now, we've seen this word a lot, altitude. We've seen it in trapezoids. We've seen it in, oh my goodness, parallel. We've seen it in every shape to this point. Well, we're also going to see it in pyramids. And altitude, by definition, is a segment that comes from the vertex to the middle of the base. And notice it says here, it forms right angles. So you see in my picture of a pyramid here, this rectangular pyramid, the base is a rectangle. So from the vertex, this blue line that I'm drawing, it goes right down through the middle of the pyramid and goes to the middle of the base. That thing right there is what we call the altitude. The other thing, the fifth thing, why did I put 2 there? That's weird. That should say 5. That's really strange. Whatever. So the fifth thing is slant height. A thing called the slant height. That is a segment from the vertex to the midpoint of any side of the base. Now I color-coded this for you. You're welcome. The slant height is this thing over here in my picture. It comes from the vertex, goes down to the middle of the actual base, the midpoint, right there, the middle of the edge, sorry, of the base. So that right there is the slant height, they call it, of the pyramid. So that's pretty cool. So this is the slant height. Nice. Now notice this though in green. The slant height forms right angles. You see the right angle symbol right there. But really if you look at this, in brown I wrote here, the slant height, here's another way to think about it. The slant height is nothing more than the altitude of the lateral face. So if you think of this triangle as a flat out two-dimensional surface, that slant height is nothing more than the altitude of the triangle. That's exactly what it is. So remember that. That'll come into play with a couple examples as well. So the idea here, again, remember, is to find the lateral surface area and the total surface area of these things called pyramids. Let's do an example. So this is actually out of your book. It tells you here the page. It is page 567, the number's 2. So the question is this, to find the lateral surface area and the total surface area of this particular pyramid. Now you notice the base that I've kind of shaded for you, that is a triangle. So this is a triangular pyramid where apparently all three sides here are exactly congruent. I'm not making it up, but that's what's in the book. And I believe it says it's an equilateral or a regular base. That's important. The base is an equilateral triangle. So to find the lateral surface area, that means I forget about the base, but I got to find the area of all three of the faces, and all those faces are triangles. In this case, all three triangles, lateral faces, are exactly the same. It's not always the case. In this one it is. But that means all I have to do is this. Let's find the area of one of the faces, only one. Because if I find that area, then I just got to multiply it by 3, and that'll give me the total, the lateral surface area of my particular pyramid. So I'm looking at one of these guys right here. I don't want to find this yet. I want to find the actual 3 triangles that are around the outside of this bad boy. So up here on the top right, I did it for you. There's my triangle. I pulled it out, 17, 17. Right there, 17. That side 17. The base is 16. So I just drew an altitude like we've done many, many times. It's an isosceles triangle, so that breaks this bad boy up into 8 and 8, which means that if I do this, that makes the height 15. You can use Pythagorean theorem with that as the hypotenuse, and that as a leg, or you could look at it and say, oh, look, it's a triple, 8, 15, 17. So I got that as the height, 16 is my base, there it is, multiply it all out, so I get 120, and that is the area, again, guys, of one of the faces. So if I take that times 3, because there's 3 faces that are the same, that gives me 360 units squared. So that right there, woohoo, is my lateral surface area, 360 units squared. Lovely. Now to find the total surface area, I got to take the lateral surface area and add that to, again, remember this script B stands for the area of the base. So I got 360 plus the area of the base. Well, again, that base is just an equilateral triangle. Ooh, I think I remember a formula for the area of an equilateral triangle. I do. I don't even have to look at my foldable. Man, I'm good. You should be too. There's your formula. S squared over 4 equals, times root 3. S squared over 4 root 3. Equals, okay. So I know the side length of my equilateral triangle is 16, so I put 16 in for S. I square that, gives me 256, so 256 over 4 attached to root 3. 256 over 4 just reduces down to 64 root 3. So this right here, guys, is the area of the base. Now, do I take that times 2 like I did with prism? Good answer. No, because there's only one base. Now, if there was 2 bases, like this, then I would take it times 2, because there's 2 bases. But there's only one. So I got it. So 64 root 3 then would be the area of the base. So I'll put 64 root 3 right there. And by the way, you take these parentheses away, units squared. This, as ugly as it is your answer. So 360 plus 64 root 3 units squared. There you go. Good luck. We'll see you in class and doing the rest of these lateral surface area and total surface area of pyramids. Peace.